So this is 2005, number 2. And you can see I've done a little bit of it already, just because it was going to take me a little bit of time to do all these calculations. I didn't want you guys to just sit there and watch me do it. So get rid of this, bring out my pen. Student is given a set of orbital data for some of the moons of Saturn shown below, asked to use the data to determine the mass of Saturn. So we want to find the mass of Saturn eventually here, probably. Assume the orbits are circular. Write in algebraic expression for gravitational force. That one's easy. Fg equals G M over R squared. That's just Newton's law of gravitation, right? Pretty straightforward. First question there. Use your expression from part A, assume circular orbits to derive an expression for the orbital period. So the point or the key to take away here is the centripetal, or because we're using centripetal motion, or we're talking about circular motion, sorry, is gravity is acting as the centripetal force. And we know that centripetal force is equal to mv squared over r, right? So our centripetal force is our gravitational force. So we can plug in here G M ms, mass of Saturn, over r squared is equal to mv squared over r. A couple things happen here, right? You'll notice we've got a mass on each side, but we've got a couple masses. This is the mass of the object that is orbiting, and this is the mass of the object that is orbiting. So those two cancel out. We also have a radius on both sides, which I'm going to substitute. I forgot to make these capital radiuses, but they are the orbital radiuses, which is capital R here. So I should be substituting that out for capital R. So we get G ms over r is equal to the velocity squared. And this is where this gets a little tricky, because we have to figure out a way to get rid of this velocity and replace it with a time, right? Because we want orbital period. We want this equation for orbital period and orbital radius. So how do I get this velocity out and the orbital period in? So the first thing I'm going to do is realize, actually, I'm going to take the square root first. So I'm going to take the square root of both sides. That would give me G, which is a constant, ms over r is equal to v. All right, and if we're talking about an object moving in a circle, and we have v, but we want to replace this with something that has to do with time, we know velocity is displacement divided by time. In this case, we're not going to use it as an actual displacement because that would give us 0. But velocity we can take as distance over time if we're talking about it as a speed, right, rather than velocity. So maybe I should call it speed instead of velocity, but speed is distance over time. So as our object is orbiting here, right, at speed v, it'll take a certain amount of time to complete one lap. And that one lap is the period, right? The time it takes to go around once is the period. But what's the distance there? Well, the distance is the circumference of this circle. So our velocity is equal to 2 pi r over the period. So we can replace that here, right? Our velocity here with 2 pi r over the period. G m over r is equal to 2 pi r over t. Make sure that goes all the way down here. So don't forget that that's a square root. And now we need to rearrange this so that it's in terms of t. I mean, technically it is in terms of t and r already, but I think we can clean this up a little bit. So I'm going to multiply t over to the other side, multiply root r over to the other side. So I'm going to get t root g ms, because that's still mass of Saturn, is equal to 2 pi r to the 3 halves, right? Because this is technically a 1/2 r, right? When we multiply it up times, we add the 1 over 1, we get, 2 over 2, we get 3 halves r. Divide the g ms over, and we get the orbital period is 2 pi divided by root GMS times r to the 3/2. There is our equation that relates orbital period to orbital radius. So which quantities, right, based on that equation that I just came up with, should be graphed to yield a straight line whose slope could be used to determine Saturn's mass? So what two quantities here could I measure or use to determine a graph or to make a graph that would give me Saturn's mass? So if I use the y as t, and if I use the x as r to the 3/2, the slope of that graph should give me 2 pi over root GMS. 2 pi and g are all constants, which means I can use that to solve for the mass of Saturn. So if I create a graph of t versus r to the 3/2, that should work out. Complete the table by calculating the two quantities. That's what I did up here. The only thing I changed for the period is I took the 8.14 times 10 to the 4th and made it 0.814 times 10 to the 5th, so that everything was in terms of 10 to the 5th. And then the orbital radius, I did take 1.85 times 10 to the 8th, raised it to the 3/2 power. So I raised all of these numbers to the 3/2 power, and that's what I ended up with. Units, meters to the 3/2, units are still seconds there. So there's D. Now we need to plot it. So I did this already too, because I thought this was going to take a little bit of time and I didn't want to spend all of that time with you watching me graph. That doesn't sound exciting. So I graphed all the points. I get this line right here. Only thing I would change, I think I wrote these backwards. I think it needs to be 10 to the 5th seconds and 10 to the 12th meters to the 3/2. So I would switch those around. But other than that, it's a graph. It works. I have everything labeled. I guess I didn't label the top. Plot the graph on the axis, label the axis and appropriate numbers. Indicate the scale. I've got the scale, but this is period versus radius to the 3/2. All right. Should put a title on there. Use the graph, calculate the value for the mass of Saturn. So first thing I want to do is calculate the slope, right? Because slope's going to be equal to, what did I say it was going to be equal to? 2 pi over root GMS. The slope is going to be equal to 2 pi over root GMS. I'm actually going to solve for this before. We'll just call this slope M, so I can solve for the mass of Saturn here. So we will multiply that up. We'll get root GMS times the slope M. I probably shouldn't be using M, but that's what slope is usually abbreviated. Equals 2 pi. Divide the slope over to the other side. So root GMS is going to be equal to 2 pi divided by the slope. Square both sides. Oops. So that we get rid of the square root. So we'll get GMS equals 4 pi squared over the slope squared, and then divide by G. So the mass of Saturn is going to be equal to 4 pi squared over M squared G. All right, so as soon as I find the slope and I can plug it in for M, I can go ahead and solve there. So slope, rise over run, I need 2 points. Pick 2 clean looking points. My line sucks. It doesn't look like there's any really clean. This is a clean point. I'll take that one. And I don't know. This one kind of goes through the half right there, pretty even. So I'll take those 2 points. So I'm going to take this point, which is 1.6, 1.7, and 4.4, 4.8, 5.2. So 5.2 1.7. And I'm taking this point, which is going to be 2.4, 2.8, 3, comma, 1. All right, so I've got my points there. Now I can do my rise over run, which is going to be 5.2, or no, that's the run. Come on, Ryan. 1.7 minus 1 over, what did I say, 5.2 over 3 minus 3. That'll give me 0.7 divided by 2.2. Okay. What did I just do? Before I forget to do it, I should put in the exponents. The y is measured in times 10 to the 5th. So this is 0.7 times 10 to the 5th. This is 2.2 times 10 to the 12th. Can't forget that. So 0.7 times 10 to the 5th divided by 2.2 times 10 to the 12th will give me 3.18 times 10 to the negative 8th. So the slope here is 3.18 times 10 to the negative 8th seconds per meter to the 3 halves. What a good unit to use. All right, and then I can take that now, right? And I can plug it in and I can solve for the mass of Saturn. So mass of Saturn is going to be equal to 4 pi squared divided by 3.18 times 10 to the negative 8th. We'll find out in a second here if I did anything right, because we shouldn't get that the mass of Saturn is pretty big. It looks like it's going to be pretty big. G, I always forget G, 6.67 times 10 to the negative 11th. 6.67 times 10 to the negative 1. Good. All right, and we'll take 4 times pi squared divided by 3.18 times 10 to the negative 8th. This is going to be a huge number, squared times 6.67 times 10 to the negative 11th gives us 5.85 times 10 to the 26th. Hopefully my units checked out and I get kilograms there. There is the mass of Saturn. All right, so there's problem number 2.